In the last video, we talked about the idea of taking some function and finding a power series that looks more and more like the function. And the key idea is to take a polynomial and find coefficients for the polynomial so that the derivatives of the polynomial match the derivatives of the function around the place where we center. For this video, we will see the definition of the Taylor series, and we'll try to understand where that definition comes from based on the example that we did in the last video. So right here we have the definition for the nth degree Taylor polynomial of a function. And right below this, we have the definition of the Taylor series. The only distinction here is that the polynomial stops at degree n. The Taylor series just keeps going. So instead of stopping at a certain number of terms, we just continue to write the same pattern. That's the power series. So where does this come from? How do we get this formula? Well, look at the pattern that we've got going on here. We're taking the function f, and in the numerators of these fractions here, we see derivatives of that function f. This is the nth derivative of the function f. In the denominators, we see factorials. Let's take a look at the polynomial that we found in example 1, and we'll see that it matches this sort of a form. So from example 1, here is the polynomial that we found as the final answer. And look at the form. We have factorials in the denominators, and in the numerators, these values were derivatives of our function e to the 2x. So we have derivative values in the numerator, we have factorials in the denominator, and then the powers of x are just incrementing up by 1. Compare this specific example to the definition of a Taylor polynomial. That's right here. Derivatives in the numerator, factorials downstairs. By definition, the first n derivatives of this polynomial will match the first n derivatives of the function at the place that we center, at x equals a. That's how this polynomial is defined. That's where it comes from. And in the Taylor series, we just continue the terms instead of stopping at degree n. Now that we have a formula for a Taylor series, we are going to start with a specific function, and we're going to write out the Taylor series, which will give us a power series that looks like the function. There's one specific case here that happens so frequently that we call it its own special name. If the center is 0, if a equals 0, the Taylor series is called a Maclaurin series. So just imagining replacing the a here with 0. If you replace the a with 0, you'll get this expression here, which is the Maclaurin series for the function f of x. Let's see how to use the definition of the Maclaurin series for example 3. In example 3, we want to find the Maclaurin series for the function e to the x. Here's how we do it. Let's start by just writing our function. Our function is e to the x, and now let's write the general form for a Maclaurin series. It's the sum from 0 to infinity of the nth derivative of the function, evaluated at 0, divided by n factorial times x to the n. The only thing that we really need to figure out in order to write the Maclaurin series for this function is the values of the derivative. The n factorial here, well, we're just taking different values of the increment, plugging it in for n, so there's nothing really to figure out with the n factorial. Same thing with x to the n. We're just taking different values for n, plugging them in, and expanding out this form. So the only thing that we really have to find in order to solve a Maclaurin series problem is to find the values of the nth derivative. In order to do that, I'm going to make a table here of the nth derivative in general, and then the nth derivative evaluated at 0. So this sort of table will set up quite a bit. We'll look at n here, and we'll look at the nth derivative of the function, and then we want to look at the nth derivative of the function at 0. We're going to try to see a pattern and see if we can predict what the form of the Maclaurin series will look like. So we'll start with n equals 0, 1, 2, 3. I think if we go to 4, we'll be able to notice a pattern. So we start by taking the derivatives of the function. When n equals 0, that's just the original function. So our original function is e to the x. If n equals 1, we're looking at f prime, the first derivative. What's the first derivative of e to the x? It's just e to the x. Second derivative of e to the x, e to the x. Third derivative, e to the x. We're getting just e to the x every single time because the derivative of e to the x is just e to the x. So that's kind of nice. Now we want to look at these derivatives evaluated at 0. This x here should be a 0. So we look at the derivatives evaluated at 0. That's where we're centering. We're just plugging in 0 into these derivative values. So f of 0, that's e to the 0. E to the 0 is 1. F prime of 0, Well, again, it's just e to the 0, which is 1. For each of these rows, we're just getting 1 when we plug in x equals 0. Now, I would like to predict what is the nth derivative at 0. Can I write an expression for the nth derivative in general when x equals 0? What will it be? Well, it's 1 every single time from this table. So for this case, the pattern is just 1, 1, 1, 1, 1. The nth derivative when x equals 0 always equals 1. So now that we've got that value, we can just plug that into the form for the Maclaurin series, and we'll have the Maclaurin series for e to the x. We simply take the sum from 0 to infinity, and the f to the n of 0, this is the nth derivative when x equals 0, that's 1. So we can just write 1 divided by n factorial x to the n. Or we could write this a little bit more neatly as the sum from 0 to infinity x to the n divided by n factorial. This is the Maclaurin series for e to the x. It's a power series whose derivatives all match the derivatives of e to the x when x equals 0. And we're going to graph this in Desmos to try to figure out where this converges. For which values of x does the power series look like the function e to the x? Let's try to figure that out in Desmos. We'll start by just graphing the function. F of x equals e to the x. And now we'll put in the Maclaurin series we just found. It's the sum from 0, and again, I can't put infinity here, so I'll just put m. And then let's add a value for m. Let's just do 1. Then we'll make this into a slider from 1 to 100. And inside the summation here, we have simply x to the n divided by n factorial. As we take more and more terms for the Maclaurin series, we'll see that the graph of the Maclaurin series, this purple graph, starts to look more and more like the graph of e to the x. Check it out. Taking more and more terms, that graph matches up with e to the x. It actually matches up really fast. So if we zoom out here a little bit, we can see how the graph of the power series matches up more and more. Now, what do you think is the radius of convergence here? We're centering at 0. So I'm trying to think through, on either side of 0, how far can I go so that this power series looks like the graph of e to the x? Well, it looks like I at least have a radius of convergence of -2 because the graph matches up with e to the x between -2 and +2. Is the radius of convergence bigger than that? I think so. As I keep going, as I add more and more terms to the power series, the resulting polynomial starts to look more and more like the graph of e to the x. The more terms I take, the more this polynomial looks like e to the x. So here the radius of convergence is infinity. As I take more and more terms, the graph of the polynomial looks like the graph of e to the x. So if I take an infinite number of terms, if I actually have a power series where there's an infinity here, the power series will exactly equal e to the x for all values of x. The radius of convergence here is infinity. Let's explore this idea of radius of convergence a little bit more. So we've defined exactly what a Maclaurin series is. We've found one. We'll practice solving several other ones. It turns out that a function f of x will equal its Taylor series, or if we center at 0, it's called a Maclaurin series. A function f of x will equal its Taylor series on some radius of convergence, which we call r for radius, around the place where we center. In the case that we just saw with e to the x, we had an infinite radius of convergence. So if r equals infinity, then the function equals its Taylor series for all values of x. We can have a finite radius of convergence. If the radius of convergence is finite, then the function only equals its Taylor series for x values between from -r to +r around the center. In some really bad scenarios, we could have a radius of convergence of 0, which means that the function would never equal its Taylor series except right where we're centering. We're not going to see any examples like this. Those are very pathological. But we've seen two examples now of these two cases. The function that we just saw, e to the x, equals its Maclaurin series, a special case of Taylor series. It equals its Maclaurin series, which was x to the n over n factorial, for all values of x. We have here a radius of convergence of infinity. We saw an example in the first video of this section when we looked at geometric series. We saw a function that equaled its Maclaurin series only for some values of x. So that was the function 1 over 1 minus x. This equals the Maclaurin series from 0 to infinity, x to the n. We viewed this as a geometric series, and we used the formula for convergent geometric series to show that this geometric series will converge to this sum as long as the absolute value of x is less than 1. So this is true for x less than 1, greater than -1. The radius of convergence in this example is 1. We can go a distance of 1 on either side of the center, 0. So we can have either infinite radii of convergence or finite radii of convergence when we create these Maclaurin and Taylor series. We are not going to worry about proving that the different radii of convergence are what they are. We'll just look at it with some examples and we'll see it visually in the graphs, but there are methods for determining exactly what the radii of convergence is for different Maclaurin and Taylor series. Let's work through example 4. In example 4, we want to find the Maclaurin series for e to the 2x. E to the 2x is the function that we used in problem 1 and problem 2, and we predicted a series for e to the 2x from problem 2 based on what we did in example 1. So what we want to do now is use the formula for the Maclaurin series to find the Maclaurin series for e to the 2x. And rather than doing this all by hand, we're going to use the series that we just found and we're going to modify it to get to the series for e to the 2x. Let me show you how. So here's the Maclaurin series for e to the x. And we saw in Desmos that e to the x equals this series for all values of x. So we can write e to the x equal to this infinite power series. Now I'm thinking of the function e to the 2x for example 2. E to the 2x, I can think of replacing the x here with 2x. So take this x value right here and just replace that with 2x and we get the function e to the 2x. So I can write the Maclaurin series for e to the 2x. Instead of going through all these steps for the function e to the 2x, I can leverage my knowledge of the function e to the x and just replace the x with 2 times x, and then I'll get the Maclaurin series for e to the 2x. So take the Maclaurin series for e to the x and just replace the x with 2x. So we have 2x rather than x raised to the n over n factorial. There we have it. This is the Maclaurin series for e to the 2x. And instead of finding it by hand, we just used our knowledge of the Maclaurin series for e to the x. Let's expand this out a little bit. If we have 2x to the n, that's the same as 2 to the n times x to the n. So we could write this as the sum from 0 to infinity of 2 to the n x to the n divided by n factorial. If you look at the answer that we found in problem 2, this is not problem 2, this is example 4 now. But if you look at the answer that we found in example 2, the function is exactly equal to this. We found the same Maclaurin series for e to the 2x. Let's work through example 5. For example 5, we are going to find the Taylor series for e to the x, but now we're going to center at x equals 1. This is no longer a Maclaurin series. A Maclaurin series must be centered at 0. So we're going to take the same function, but now we're going to center at x equals 1 and see how to find the Taylor series for f of x equals e to the x centered at x equals 1. Let's write down our function. Again, we have the function e to the x, and then we will write where we center. We're centered at a equals 1. Now let's write the general form for a Taylor series centered at a. It's the sum from 0 to infinity of the nth derivative evaluated at a times x minus a raised to the n divided by n factorial. A here is 1, so let's replace the a's with 1. So this will be the sum from 0 to infinity, the nth derivative at 1 times x minus 1 to the n divided by n factorial. Once again, we don't have to do any work to figure out anything with this portion of the expression. The x minus 1 to the n over n factorial, that's all predetermined. What we really need to do is find an expression for the nth derivative of the function at 1. So just like we did with example 3, we will set up a table to try to find an expression for the nth derivative when x equals 1. So we'll look at the nth derivative in general, and then we'll look at the nth derivative at a equals 1, the place that we center. And we just need to take enough values here so that we can notice a pattern. So we'll go n equals 0, 1, 2, 3. I think we'll notice a pattern if we go that far. So the 0th derivative, well, that's just the function itself. So the function itself, e to the x. And again, we're just taking derivatives of e to the x. So the derivative of e to the x is always e to the x. We get e to the x every single time. Now let's plug in 1. Well, f of 1 is e to the 1, which is e. And then f prime of 1 is e to the first, again e. We get e every single time. So the nth derivative at 1 is always just e. Let's just write that down. The nth derivative when x equals 1 will always equal e. So what is our Taylor series here? We're just going to replace this portion of the Taylor series with e. We have e times x minus 1 to the n divided by n factorial. We could even take this e out of the sum. This sort of works like integration. If you have a constant inside an integral, you can take it out front. The same thing works with summation notation. If we have a constant inside of a summation, we can take it out in front of the sum. We don't have to do that, but we could if we wanted to. This right here, this is another expression for e to the x. The radius of convergence here is also infinity. This is not a Maclaurin series because we're not centered at 0. We're centered at 1. So this is a Taylor series centered at 1 for the function e to the x. Let's briefly take a look at this in Desmos. Here's our function e to the x, and I've already typed in the Maclaurin series that we found in a previous example, and here's the Taylor series centered at 1. The only difference here is that these two different power series are centered at different places. They're both going to look more and more like the function e to the x. They're just centered at different spots. So the Maclaurin series, that's centered at 0, and notice how the graph of the polynomials that we're getting here, that matches e to the x when we're close to 0. Now, if we add in the Taylor series that we just found, centered at 1, that graph is going to look like e to the x when we're close to 1. Here it is. So as I take more and more terms for this polynomial, that will match up with e to the x around x equals 1. So it's not the greatest fit near x equals 0, but near x equals 1, it matches the graph really well. The Maclaurin series is centered at 0. Here's the Taylor series centered at 1. Both of these power series will converge to e to the x. They're just centered at different locations. And we can see how they both converge simultaneously if we do this. That's super nifty.